So with that out of the way, let me just tell you what we'll be covering because the notebook materials that we have are much more extensive than we have time to cover. So if you're following with the materials that you find in the link in the chat, you will have access to all of these, well, 6 notebook and 1 Wolfram language file. In this webinar, because we only have about an hour and a half, we only have time really to cover one of those notebooks. So what we're going to focus on is the example function notebook, where we'll essentially be creating a single function, but we'll be putting everything that we could possibly put into that function. The other notebooks that you see in the materials go into specific details about a single thing. So the first function is mainly about, the first notebook is mainly about arguments that go into a function. The second notebook is about options and so on. So if you're interested in any of these topics in more detail, or if there's any of the topics where you feel like you need a bit more help or some more resources to help you along, then you are obviously more than welcome to explore that at your own pace. But as far as our webinar today is concerned, we'll only be covering the example function notebook. Cool. So what are we going to do in this notebook? As I mentioned, we'll be creating a single function with everything that we could possibly put into it, going into it. So before we start doing that, let me show you what the end result will look like. So let me just evaluate all of these lines of code that you see on the first slide here, just to show you what our function will be able to do once we have finished putting everything together. So it's a function that will take an image. So it's an image processing function. And one of the things it's going to do is it's going to apply effects to that image. So things like blurring the image. So this is the image. First of all, this is the image that we'll use as an example. It's part of the example data that we have in Wolfram Language. So the first thing, one of the things we will be able to do to that image is apply a blur effect. And you can see the first output is the same image, but a bit blurred. Sharpen effect, RGB effect. We'll be able to specify options for each of the effects. So for example, if we are blurring the image, we'll be able to specify the radius of the blur effect. If we're sharpening the image, likewise, we'll be able to specify the radius of that. If we are modifying the red, green, and blue channels, we'll be able to specify the multipliers for each channel. So in this example, we're multiplying the red channel by 3, which gives us this kind of redified image. Green channel by 2, and we're leaving the blue channel alone. So we'll be able to apply effects and specify options for that effect. We will also be able to take an independent option, independent of our effects. So in this case, we'll be able to do grayscale on the image, as well as custom options. We also will make sure that our function inherits all the options that are available on the built-in image function that's in Wolfram Language. So we'll be able to do things like image size and resize the image with that, which is an option that's available on images, and we'll just inherit that for our own function. One thing that's also very important, that's frequently overlooked, is how the function handles how the function is robust to bad or no input. So when we provide the function with a bad image or some extra argument that shouldn't be there, some bad option and so on, how our function handles that. And ideally, we want our function to handle that by giving the users, whoever is using the function should ideally receive a descriptive error message telling them what went wrong and how they can what they can do to fix it. So we want things like bad image is not an image. For example, if somebody just passes something that's not an image, too many arguments, options, and so on, instead of just simply saying, there's an error, please try again, or something like that, which unfortunately is becoming very common everywhere on the web, but we'll make sure that our function does better than that. And finally, there should be a convenient way to extract information from the function. So information might be how the function is used, what styles are allowed, what options exist, and what are the default values for those options. So if we don't specify those options, what do they default to? That information should also be easily available to the users. So we'll create this kind of information sheet for our function. There are a few more things that we'll do mainly towards the end, but that is basically what we are working towards. So we'll start with, as I mentioned, from the very basics. You're starting about talking about arguments, restricting arguments, options. And then later on, we'll move on to some interesting concepts where, as I mentioned, even if you're an experienced user of Wolfram language, I believe you'll find useful things like overloading and so on. So if the webinar seems a bit too simple at the beginning, please stick around, as I think there is something for you towards the end as well. Okay, so the idea is that we are going to clear this image. So I showed you what the function will look like at the end. We'll clear that definition and we are going to start and build it from scratch essentially. We're clearing, so we're starting with an empty definition and we're building our way towards that. So before I get into the content, just something I forgot to mention at the beginning. If you have any questions, like always, feel free to put them in the Q&A tab. On Big Marker, I'm also keeping an eye on the YouTube live chat. If you have questions, feel free to ask them there as well. And I'll do my best to answer the questions as I go through the materials. Or if I don't have the answer for you right away, I'll make sure to contact you by email after the webinar. Cool. So let's start building our function. So our function is going to be called image styler, and it is going to take two arguments. It's going to take image and style. But before we get into discussion of arguments, let's just look at this whole function definition here that I have highlighted on my screen. Maybe I should make that a bit bigger as well, because we don't have much code at this point. So what you're seeing here is the function definitions, and there are a few important things to point out. The first is obviously the function name, in our case, image styler. Just a note on conventions, we use camel case for function names. So you see image starts with a lowercase I, styler starts with an uppercase S. You can, especially if you're writing your own functions, you can name them however you want, but that's just a point of convention. Then after the function name, we have a list of arguments. Now, this could be one argument, two arguments. It could also be zero arguments, which is something we'll get into a bit later. But in this case, we have a list of two arguments. They're separated by a comma, and each of them has a name. So the first argument is called image, and the second argument is called style. The interesting thing to mention here is this underscore that you see that goes after the name of each argument. So underscore, for now, we are going to leave it mostly unexplained. But what I'm going to say about the underscore is that it says that the arguments could be of any type. Basically meaning that image could be text, it could be a number, it could be an image, it could be a video, audio, and so on. This underscore stands for any Wolfram language expression. So as we have defined this function now, then these arguments could be anything and the function will be valid for them. Now you can immediately see a problem with that, because if an image is not actually an image, but it's, let's say, an audio file, then we actually don't want that function to be defined, because we'll be applying blur effects and we'll be applying sharpen effects. We'll be modifying color channels, and obviously those things only apply to images. So ideally, we want our function to only accept images, and we'll build that into the function. But in the most simple case here, we are leaving it open to any type of input. Same goes for style. At the moment, style could be any Wolfram language expression. So those are the arguments. Then we have this little colon equals, or walrus operator, as it's known in some languages. In Wolfram language, that stands for set delayed. Again, without going into too much details into what this does, at the moment, we can just say that it allows us to provide a definition without actually evaluating anything. But when you're defining a function, you always use this walrus operator. And then on the right hand side, we are simply defining what our function is going to do. And in this case, let's break down what our function is doing. It's creating an image where a style is applied to image. The only interesting thing to mention here is that we are using the names of the arguments of the function. So here, because we have named our arguments image and style, we can use those arguments here. Basically, this means that whatever image is passed into the function is the image that gets applied here. Whatever style is passed into the function is the style that gets applied to that image. So that allows our function to be more generalizable. And again, those are just names. So we could have easily had x and y, and then on the right hand side, we can define x and y. But again, a point of convention is to name your arguments in a more descriptive way rather than ABC or XYZ and so on. So our most basic function takes two arguments and applies a style to an image. So we can define that and we can move on. So um, to apply the styling in the second argument, we'll create some helper functions. Helper functions are very common when your main function is doing a lot of things. You want little functions that could be called by the main functions um, that do simple things. So instead of putting everything into one kind of monolithic 5-page long function, you break it down into multiple functions, and you call the functions from the bigger functions. In this case, we are going to define three helper functions. So the first thing, so just to take a step back to say what we are trying to achieve here, the first thing we want to achieve is we want to be able to apply three different effects on the image that the user passes in. The first effect is blur, the second is sharpen, and the third is RGB. So what we are going to do is, in this case, even though it's not the optimal way to do it, we are going to use a switch statement. So let's break down and see what's happening here. Again, we're defining our function. This part is the same as the previous part, and we're generating an image. Now, in this case, we have this switch statement. Switch statements, if you're not familiar, operate basically like if statements, and they check if a specific condition is met, then something is done. In this case, let's break down the switch statement in plain English. We're saying we're switching on style, so we're essentially applying an if condition to this style argument, and we're saying if style equals to blur, then execute the following thing. The following thing being, in this case, call the blur function, which doesn't exist at the moment, and that will be one of our helper functions. But we're saying if the style matches blur, execute this blur function on the image. Else, if style equals to sharpen, then call the sharpen function, which again doesn't exist at this point, but call that on the image. And if the style is RGB, then call the RGB function on the image. The last interesting thing here is this blank or this underscore here, which means if the style is anything else that is not matched by either blur, sharpen, or RGB, simply return the image. So don't apply any style to it, just return it as it is. So even though technically it's not the most clever way of doing it, hopefully it's readable enough so you can see what we are trying to do. But the first thing that we're doing here that is nice is that instead of hard coding the logic of all of these functions inside our main function, we're breaking them down into helper functions. So let's define that, and let's see. At the moment, while we still don't have the helper functions, let's see how this works. So we're defining this function, and then we can test it. Here we have 4 simple tests where let me just show you what test image is. In test image, we have stored our example image that we'll use throughout the webinar. It's just a simple variable that holds an image. So here we are calling our function with that test image. So the image input is actually correct. and we're saying that we want to blur this image. So let's go back to our function definition and let's trace what is actually happening when we execute this command. I can have both of them on screen. Okay, so we are saying that the image is test image. That's absolutely fine because our image argument accepts anything anyway. And for style, we are passing the string blur. So when we execute or when we evaluate this statement, what happens is we go inside the body of the function, which goes in the switch statement, which checks the style argument. Because the style argument here is blur, then we match here in this branch. So what switch does is because we match blur, it executes this blur function on the image. So what happens when we do that? Well, at the moment, blur function is not anything. We haven't defined what blur function actually is. So we get a weird error here that is actually not very helpful, but it's basically saying that it cannot execute that function on the image. Likewise, when we say sharpen, it tries to execute sharpen function. Because at the moment it's not anything, we'll get an error again. RGB, same idea. Although when we pass bad style, so when we pass something that doesn't match either blur or sharpen or RGB, we get into this blank underscore which matches everything, and the switch statement just returns the plain image. So in the last case, when we pass something that is not caught by our switch statement, we simply get the image back, which is what we wanted anyway. So that part works fine without us having to do any extra work. Cool. So the next thing we're going to do is we are obviously going to apply, we're going to define our helper functions. In the case of blur and sharpen, so the first two effects that we want to cover, we are lucky in the sense that Wolfram Language already includes functions for those effects. So we don't really have to write our own custom functions. And just to show you what those functions are, for blurring images, we have blur. This is available just in plain Wolfram Language without any custom contexts. So blur takes an image and it takes a radius of the blur effect and it gives you back the image but blurred with that radius. Straightforward. Same idea with sharpen, takes an image, takes a radius, gives you back the image. Now, for the third, so we can use those right away. We don't need to write our own custom functions because those are already, we kind of get those for free from Wolfram Language. For the third argument, we do need to write our own custom function because we want to do slightly more complicated. We want to take the red, green, and blue channels in our function and we want to multiply them by specific values. So there's no built-in way in Wolfram Language to accomplish that. So what we're going to do is we're going to write our own logic and we're going to write our own helper function. We're going to call this function RGB style. And let's look at what arguments it takes because it's a bit more interesting here now. The first argument, image, fairly straightforward. The second argument that our function takes is a list. And it's a list of 3 values, obviously one for each color channel. So we have red, green, and blue. We have our typical set delayed / walrus operator. And on the right-hand side, we have the functionality of our function, if you will. So what it's doing essentially, it's breaking up the image into 3 channels based on RGB, and then it's multiplying each channel by each of the values that we provide in the list of our arguments. So easier to explain when we actually test it. So once we have defined this function, we can call it again with our test image. And in the list, we provide the following arguments, 3, 2, and 1. When those arguments go into the function, into the body of our function, each one is multiplying the corresponding channel. So here, what we are doing is we are multiplying the red channel by 3, the green channel by 2, and we're leaving the blue channel as it is, or multiplying by 1, which is the same thing. And we can test if we have a very high value for the red channel, you see that the image becomes even more red. If we multiply the blue channel by a lot, then image gets more blue and so on. So a slightly more complicated helper function, but still still staying in the realm of what we already know. Just take some arguments and apply some functionality to those arguments. Cool. So now that we have the helper function for RGB style and we have the built-in functions for blur and sharpen, we can integrate all of those three things into our function, into our image styler function, and we can make it work, at least on a very simple level, on a level of either applying one of three styles. At this point, with hard-coded values for radius and color channels, but we'll fix that as well. But at this point, we can say that our function can take any image and it can apply any of these three effects to that image: blur, sharpen, RGB. If the user asks for anything else, just return the plain image. We can't do anything else at this point. So just to quickly cover the switch statement again, checking the style. If it's blur, then we're calling the built-in Wolfram language function. Likewise with sharpen. Um, if the user requests RGB styling, then we call our helper function. So you can see that instead of defining the helper function here, it keeps our code nice and lean and readable. Cool, let's define that and let's test it again. So we're doing essentially the same tests that we did previously, but this time because we have defined, instead of having placeholders for our helper functions, now we've actually defined them. So our function is able to handle all of these inputs correctly. Good stuff. And as a bonus, the function deals with some bad inputs as well. So just like in the previous example, if we pass a bad style or a style that doesn't exist, a style that's not defined in our function, we get the image back. Um, but other bad inputs, such as providing an image or providing anything else but an image to the image argument, results in an error. And it's worth just spending a minute here saying why this happens. So let's see what happens when we call this specific line of code. We are providing bad image as the first argument. So what is bad image? Bad image is not anything at the moment. So it's not a variable. It's not. It doesn't hold any value. It's just a symbol that we made up, and we're passing it to the first argument of our function. And we're saying I want to blur bad image. Going back to our definition, because the style is blur, the switch statement matches this string and it applies this function. So bad image gets passed here um, to the blur function with radius 10. But blur function only accepts images, which is what our error message is saying, expecting an image or graphics instead of bad image. So we need to handle that as well. But at the moment, it's our function is not very robust to the first argument being not essentially not what we expect. Cool. So the next logical step that we are going to take is to restrict the argument. What do we mean by restricting an argument? We mean that we only want our function to be valid if the argument is of a certain kind. So in the case of our function, it's pretty obvious what we want to do. We want to say that the first argument image should be an image, and the second argument style should be a string. So let's look at how we can actually accomplish that in our function definition. Again, very similar function definition previously. The changes from the previous slide are highlighted in orange to kind of help you see what has changed. But the basic change here is when we define our arguments, instead of having the simple underscore, which means that this argument could be anything, we have the head that we want the argument to be. Now, what is the head? That's a kind of a Wolfram language term that may not be immediately obvious. But basically, so it's worth again spending a minute here just to say what we mean by head. And the basic idea is that every expression in Wolfram language has a head. And if your expression is, let's say, 2 plus 2, then this thing has a head, which is an integer, because this returns 4. If your expression is a string, then it has the head of a string. If it's an image, it has a head of an image, and so on. And so you can think of it as types, especially if you have experience with other programming languages where there might be typing systems. You can think of heads roughly as types. They're not completely identical, but it basically tells you essentially what the expression is. And the nice thing about having heads or having types is that we can match those we can match against those types. So here we're saying the first argument should only be a thing that has the head of an image. If you pass anything else that doesn't match that head, then this function is not valid. Likewise, with the style argument, we want that to only be a string because in the switch statement, we're matching against strings. Anything else is not valid. So we want to restrict the style argument as well. Now, technically, with the function as we have it now, we don't really need the restriction on the second argument because this underscore already catches anything that is not one of these three strings anyway. But just for completeness, we are restricting that argument as well. So essentially, what this underscore is going to catch now is any string that is not one of these three strings. So if the style argument is something like highlight, then it's not either one of these three strings. So it's going to match the underscore, and we're just going to return the plain image. If the bad style is something that is not a string at all, so if we pass again an audio file, then this function is not going to evaluate at all because it's expecting a string argument. So it's not even going to go inside the definition. Cool. So let's define that. So the RGB helper function should, we can also restrict the arguments in our helper RGB style function. So what do we want there in terms of the arguments? What should they be? So the RGB helper function should only accept an image, obviously its first argument, and it should accept a list of 3 positive numbers. So because again with the RGB style function, we are multiplying each color channel by a number, and those numbers should be positive. So we don't want to be multiplying the red channel by -10. Even though mathematically that works, but just for in the interest of parsimony, we want our multipliers to be positive. So how do we do that? So technically, -1. So if we go back to the idea of restricting by head, let's look at the head of these two expressions. So the head of -1 and the head of 1 are both integers. So that's not very good. So because we only want to get positive numbers, we don't want to get negative numbers. Restricting by head doesn't help us in this case because they both have the same head. So what we're going to do is we're going to have a slightly more complex kind of pattern that we're going to restrict by. So for convenience, we'll make another small helper function to check that an expression is both numeric and positive. So let's see how we do that. So we're defining yet another function. So now we are 2 levels down. We have an image styler, which calls RGB style, and RGB style is going to use another function called positive number q in its arguments. So let's look at what positive number q is doing. Again, it's a function just like any other function, so we can read it very easily. We can see that it takes one argument called expression, and it checks that 2 conditions are true, which is what this AND function stands for. It's checking first whether the expression is numeric. So just to show you what numeric Q does, it takes one argument, and if the argument is a number, it returns true. If the argument is a string, it contains false. It returns false. So the first thing we want to do is to take the expression and see whether numeric Q returns true for that expression. And the next thing we're going to do is we're going to check whether this true Q statement also returns true. So again, let's copy that here so we can see how it works. So remember, any argument that we pass to this function is going to take the place of expression. So let's say we pass 1. Essentially, we're checking is 1 greater than 0. Obviously, that's true, so the function returns true. If we pass -1, then this function is going to return false. So essentially, with positive number q, we're checking that both of these functions return true. It's numeric, and it's also greater than 1. Cool. So we have our helper function, but how do we actually incorporate that into the arguments, into the argument restrictions? The first thing we do is we want to make sure that in this function as well, image is always an image. And then in the RGB values argument, instead of having underscore and the name of the head, we want to use a slightly more complicated pattern that we are going to match against. And this pattern is defined by having a colon, and because we have a list, I'll just read all of this definition in plain English. Essentially, I'll translate it to English. So we're saying that we want repeated number or 3 of something that matches or something of which positive number q returns true. And then on the right hand side, we have the same functionality as before. Just looking at the Q&A chat, Jan is asking, why do you use true Q instead of just inequality? That would work as well. It's just that true Q is a bit more descriptive at this stage. But you could definitely just use greater than. Let me copy this. You could just have this condition, and that will return true as well, or it will return false. So you could definitely do that, but this is a bit more kind of verbose and easy to follow, probably. So now that we have kind of modified our RGB style helper function, we can test it again. And the way we're testing it, we're passing a test image, and here we're passing a bad style. Now, what you see the output of this is this is essentially the Wolfram language way of saying this function does not exist. But why does this function not exist? After all, we're just calling image styler. We have defined at this point just multiple times in our notebook. So what is Wolfram language telling us when it's returning us this function itself? And the reason is that when we are restricting by arguments, we are essentially saying this function is only valid. This function only exists if the first argument is image and the second argument is string. If these arguments are something else, then this is not the function that the user is looking for. In other words, it does not exist. In other words, just return whatever they gave in. And that will be more important when we get into things like overloading, because we can create function definitions for different sets of arguments, different types of arguments. But at the moment, the way you can read this, whenever we restrict the arguments, we are saying that this function only ever exists for this type of argument and this type of argument. For any other types, just assume that it does not exist. One practical benefit of that, now our function is still quite simple, but if you imagine on the right hand side, we had some computationally intensive workflow, then we don't if the arguments are not what we expect them to be, we don't want to go to the right hand side and run the expensive computation for nothing. It's much better at that point just to say to the user, hey, the function you're looking for doesn't exist. um, and again, this is better done with error messages than by simply returning the function itself, but at this point, it's good enough. Just to make the code clear, yeah, I think that for the true queue, it's just to make this piece of code a bit clearer. If it's easier for you to follow it like this, then that will work as well. So um, it's equivalent. Okay. The next thing we're going to do is we are going to have optional arguments, and we're going to have default values. So far, we have always had two arguments in our function definition. Um, and we have always provided two arguments when we have been calling the function. Now, in many cases, you want to have default values. Um, you want to provide the ability to the user to provide a value, but if they don't, you want to assume some sensible default. So let's look at what the syntax to do that is in Wolfram language. Again, the only change here is marked, it's kind of highlighted in orange so we can see what we're doing. Again, we have our two arguments, image is an image, style is a string. But now after our second argument is defined and we're restricting by its head, we have this column notation, which goes to the default value that's going to take if the style string is not provided. In this case, the default value for style is dummy, which again is nothing, it's undefined. So what this essentially does, what this means is that if the user doesn't provide any style, then we are going to replace the style argument with this dummy value. Because dummy is nothing, it's not going to match any of these conditions. It's going to go to the underscore, and we'll receive the image back. However, putting in a dummy value like that is a bit of a hack. It's not really good practice. If all you want to do is to say that um, we don't know how to deal with that style, here's your image back. Um, a nicer alternative is to modify the argument restriction to allow an automatic style. So many functions in Wolfram language have an automatic option, and what we are going to do here is we are going to restrict our style argument to say it could be either a string or it could be automatic. If the user doesn't pass anything, then we assume that they meant automatic. And that's going to be handled much more gracefully in our functions down the line. So, worth lingering very quickly on the notation here. Now, instead of restricting simply by head, we have again a slightly more complicated expression. So again, I'll read it to you in plain English because the syntax might not be immediately obvious. We are saying that we have something, um, what this underscore represents, that matches the following expression. Um, so everything that goes into the brackets is what we call a predicate, or it's a function or an expression that returns either true or false. And we're saying, in this case, we're saying if whatever is passed into here returns true, then our function is valid. If it returns false, then our function is not valid. Because we have a default value, it means if whatever goes into here returns false, then we assume that the user meant automatic, or the user wants automatic. So what is inside the brackets here? It's a pure function. You can recognize it by this ampersand notation at the end of the function. And it's a function that checks whether the argument matches something. So the slot here is the pure function way of saying an argument. And we're checking whether this argument matches either a string. So again, this is essentially the same as saying style underscore string, but in this case we have it here. Or, and this vertical bar stands for or. So it's either string or automatic. Um, so if the argument is either string or automatic, this match q will return true. Then our style is happy. Then we go into the function. If this match q returns false, then we assume the default value, which is automatic. Hopefully that still makes sense. So let's define that, and we can do we can give some default values to our RGB style function as well. In this case, we'll simply provide a list of 111. Essentially, we're saying that um, if if the arguments that the users provide don't match um, this condition, which is a list of three positive numbers, then we're just going to assume 111. In the other case, we're not going to make any changes to the colors of the image. So let's define that as well, and let's do a little bit of testing. Now, when we only provide one argument to the function, our function works. Again, let's see why that is happening. It's basically because we have a default value for our style argument. So in this case, when we pass in test image without any style, this automatically goes to the default, which is automatic. So calling this is essentially the same as calling that. It's just that this automatic gets inserted by our default value. And we can call it explicitly, and we can see that the result is the same. So because automatic is not called by the switch statement, it goes into the blank underscore, and we just get our image back, no styles applied. Um, Likewise, our RGB helper function will also accept either one or two arguments. And again, the reason for that is that if we don't provide multipliers for the channels, then our function now assumes that we mean a list of 111, which multiplies each channel by one, which doesn't do anything, so we get our image back. If we do have multipliers for the channels, um, then obviously those still get applied correctly. So our function is now a little bit more robust to bad input or input that doesn't include all the arguments, because some arguments we can safely handle with default values. Cool. So the second big thing um, that we can add to our functions other than arguments are options. And options, you will have seen plenty of options when you've used just normal Wolfram language functions. It is these sets of rules that get applied to function, and we'll look what the we'll, we'll have a look at what those look like in a little bit. But just as an overall view, there are three types of options that we want to implement for our specific functions. We want image options. So again, because our function is dealing with images and Wolfram language has an image symbol which already has a lot of options, we want to make all of those available in our function as well. We want style options. So when we call something like blur, we want to say, I want this image blurred with a radius of 15 or a radius of 150. So that's another option that we'll be able to call, that we want to be able to call. And finally, we want kind of an independent option that is called grayscale. So independent of blurring or sharpening or changing the color channels, we also want the users to pass in a grayscale option, which should return a grayscale version of their image. So let's tackle those one by one. Let's start with inheriting all the options that Wolfram language has on images. So there is again a little bit of syntax here. Whenever we want to define a list of options for our functions, we call this options function. And inside we pass our function that we want to define the options of. And this options is already available for all the built-in um, all the built-in functions of Wolfram language. So just to demonstrate that, we're taking an image, which again is a built-in symbol in Wolfram language. You can inspect the documentation, you can see what it does. But when we call options on that image, we get a list of rules. So we see that for the built-in function image, Wolfram language can accept alignment point, which by default is the center, baseline position, which by default is automatic, and so on. But basically, the structure of options is a list of rules where each key in the row is the option and each value is the default for that option. So basically, this is what Wolfram language, these are all the options that Wolfram language has for image. And we want to make those available for our function as well, because now we're only accepting images in our function, then we can safely assume that all of these options will be able to be applied correctly, and we're not going to get any errors. So the first thing we do is we are saying that the options of image styler will be equal to the options of image. Essentially, we're getting all of the options of image and we are assigning them, uh, we're kind of stealing them, if you want to look at it that way, from the options of image. Now, the other thing you need to do to make sure that your function accepts options is to have options as the final argument in your function, um, where colon goes to options pattern. Again, that's more of a quirk of syntax than something that will make intuitive sense to you. Um, but options are technically arguments in a function. They're just slightly different than your normal arguments, in that they take this option pattern expression. And then finally, you can include them at the end of your function. So here again we have our image function. Switch statement is the same, and finally we say that we're going to apply the options um, that we defined here. We're going to allow them to be in the function as well, so that if the user does pass an option, they get inserted into the function. So um, So with our definition here, we have inherited all the options of image, and our function is now able to receive those in the third argument, and it's able to apply them to the image. What we want to do is we also want to define, other than the options that are available on image, we also want to define our custom options as well. So again, going back to what options are, they are simply a list of rules. So what we can do to define our custom option is to provide us a list of rules and assign them to the options of our image styler function. In this case, um, we want to define radius, which by default is 2, and we want to define RGB values, which by default is a list of 1, 1, 1. And we're joining those custom options with the options on image, essentially making sure that our function accepts all the option on image as well as our custom options. Um, and just to see what that looks like at this point, if I can evaluate that, just to show you. So all of those, so here we're checking what options our function is able to understand. And we have all the options that we saw in the image function, and we have all of our, the 2 additional options that we added ourselves here. Finally, we want to add a grayscale option. And for that, we are going to define another helper function, which is again just a function, fairly simple one as well. So here we have the grayscale function, which takes an image as the first argument, and it takes a boolean as a second argument. Here we are simply checking whether the second argument matches this boolean q. In other words, if we call it separately, you can see that if we have a true or false, then the Boolean Q will return true. If we have anything else, then this will return false. And then in terms of the actual body of the function, it's a if statement. We're checking whether our Boolean is true, because even so, if we pass false, um, the boolean q returns true, so the function is valid, but we actually want to check whether the user passed through. Um, it's probably not the best way to explain it, but hopefully it makes sense by looking at the code. Oh, there's probably a better way to write it as well, but hopefully this makes sense. And we're saying if the second argument is true, then we are going to apply this function color convert to the image with option grayscale. If it is false, we're going to return the image as it is. So we're not going to grayscale it. Okay, so let's define that. And let's add our final custom option here, um, which is going to be gray Q. And by default, it's going to be false. So unless the user specifically requests gray Q, we're going to assume that it's false. And false will get passed here. Um, and it's simply not going to match in the if statement. So we're just going to return the image by itself. Let me just have a look if there's anything I'm missing. I believe this is it. So again, once we have defined our custom options, and again, we're joining those up with the options of the image function as well. So here we can simply modify our code. And again, this is not the most elegant way to do it, but we're wrapping our whole function in grayscale now. That is going to check the gray Q option value. And again, if it's true, it's going to go in our helper function, um, grayscale. And if it is false, then we're just going to get the image back. So essentially with this grayscale function, because remember, if we go back to our definition, the grayscale function takes two arguments, an image and a boolean. So what we have here is we are saying that this whole thing is going to be the first argument that gets passed to the grayscale function. It's simply going to be an image. So the style will get applied, and then the resulting image will get passed as the first argument to the grayscale function. And the second argument is simply going to be true or false, depending on what the user specified. Or if they didn't specify anything, then it would be false, uh, because that's the default. Cool. So again, we have a bit of testing, but I just want to make sure that this is clear as well, because the syntax is getting a bit unwieldy at this point. We'll clean it up a bit later on. But hopefully the concepts of what we are doing are clear enough, because the syntax, you can always look back on it and kind of get used to it, especially with defining options. It takes a few times of you actually doing it, to get used to it. But as long as you understand what we are doing conceptually, that we're restricting arguments and we're defining a list of rules which are options, then we are good at this point. So once we have defined all that, let's test it. Um, so the first test we have is, again, we're passing our image and we are passing an option in this case. So we don't have a style, which is fine because style has a default value now, but we are passing an option. Um, and that option is image size. So going back to our option definitions, here we didn't specify image size. So it's actually an option that comes from the image symbol, from the built-in options of the image symbol. So because we inherited those for our function, we are able to use it just as if we defined it ourselves. And image size obviously resizes an image with a specific value. I believe it gets applied to the width of the image. So here essentially we are saying I want the test image resized so that its width is 40, and this is what we get back. However, at this point, the custom styles don't work because they're being fed into image. So here, if we pass blur with radius 1, at this point it doesn't work because radius 1 gets passed to the image. So we need to fix that. But we have successfully gone, let's say, halfway through in kind of inheriting the options of image itself. Um, Jan is asking, could it also be boolean underscore question mark boolean q? Yes, I believe that is what it was. Let me have a quick look. Boolean, boolean. Oh, you mean without the colon? It's so when you have predicates, you let me just make sure that that's what you meant before I go into explaining. Yes, when you have predicates, you have to kind of preface them with the colon. Um, so again, that's another kind of quirk of syntax that takes a while to get used to. But if you're simply restricting by head, then you don't need to have the colon. But when you have more complicated predicates, then you do need to preface them with the colon. Um, at least that's what it was until a few versions ago. But I see that this is not complaining about syntax, so it might actually be worth testing if that's something that's been added. But just to be safe, here we're using the full kind of syntax with the colon. Cool. So now we are going to clean up. We're going to start cleaning up our function a little bit. And the first thing we're going to do is we are going to remove duplicated options. So the options that are not part of image can be deleted. So again, the way we're going to do this is we are going to handle that. We are going to handle that in the actual body of the function itself. So here we have our um, option of image styler. We already looked at that. I showed you what that looks like previously, but this is what it looks like now with our custom options and um, with our options that we inherited from the image symbol. Um, so what we are going to do in our options is we are going to delete those cases that don't match either one of those values. Um, so we're looking at the options that we are passing in, and we are saying that we are going to delete the options that are not part of the image function. So radius, RGB values, and gray Q. So let's define that, and that makes sure that our grayscale options and the grayscale option itself and our custom options, blur, sharpen, RGB, also work correctly alongside the functions from image. So you can see when we test this with the blur, we can specify radius and that works correctly. When we test with sharpen, likewise, RGB, likewise, and RGB, and now with gray Q, we can pass also a Boolean, which grayscales our image. If this is false, it's just going to return the image itself. So that works correctly. Um, however, so what we have achieved um, until now is we have our custom options living happily alongside the options of image. What we are not accounting for at this point is there's no restriction on bad options. So there's restrictions on bad arguments. So as we saw previously, when the image is not an image or the style is not a string, then we kind of handle that gracefully. But then we added options, and at the moment we're not handling bad options gracefully at all. So we can test if we pass some bad option or an option that doesn't exist, and we provide some value, then we get an error message. Unknown option, bad option in image. So um, instead of deleting options, it is better to filter them. And essentially what we are going to do is we're going to filter options such that we are only applying options that actually exist instead of trying to apply options. So in our previous test, because this option gets to the body of the function, our function actually tries to apply it, and that's where the error message comes about. So what we're going to do next is we're going to make sure that we're only trying to apply an option if it actually exists. So again, a little bit of syntax here, but essentially we're using filter Um, so we are essentially we're saying only apply these options that are in options of image. So anything else gets filtered out, and we're not trying to apply it. We're not generating these error messages. So let's define that. And oh, there are no tests here. I think there should be tests, but we are probably going to do a few more. Oh, yes, yes. So conditions. So just like we were restricting arguments either by head or by predicates, we can also restrict options with a slightly more complicated pattern. And that slightly more complicated pattern is a condition. So restricting by head allows us to only look at the head of the expression and see if it matches. So a very, very simple way of restricting things. Restricting by Boolean allows us to specify any function after this. After this notation, it allows us to specify any function that returns true or false. So that function could be um, like a built-in predicate, like numeric q, for example. In fact, every Wolfram language function that ends with q returns either true or false. So we could insert a simple one after that, or we could write our own. As long as it returns true or false, we can use it in this way. But what happens if we want to have even more complicated conditions by which to match either our arguments or our options? That's where the condition function helps us to specify our custom logic. It, it allows us to specify our custom logic to restrict, again, either arguments or options. So a new bit of syntax here. So let's actually, this is probably easier to read if I have this on one line and then this on a separate line. So let's look at what we're doing here. We have our image styler function. We are taking our arguments with our usual restrictions. First argument restricting by head, second argument restricting by predicate. Our options is just an option pattern. Now, before we get into the set delayed walrus operator, we have an additional piece of syntax here, which is the condition. So the first thing is this shorthand, which is a slash semicolon, which if you hover over it, it should tell you that it's a condition. So we're saying we have our arguments, we have our typical restrictions, but we also have an additional condition by which we want to restrict those arguments. And everything that comes after the slash semicolon is the actual condition that you want to match against. And in this case, we're checking whether the options that the user passes are contained in the option of image styler. Basically ensuring that if the user passes an option that fails this condition, then we're going to say that the function is not defined. Again, this is doing a similar thing that we did previously, where we're saying that if the argument is not of the expected type, then we're going to say that the function is undefined. Here, we're saying if this condition is not met, then the function is undefined. In this specific case, the condition is whatever options are passed are contained in the options of image styler, but this condition could be anything you want. Then inside the actual body of the function, we're not doing anything else. We're simply applying our styles. And as I mentioned, in the when you have a condition after the arguments, that can be as complicated as you want it to be. So in this case, we have a few more conditions, and with this, when we use this AND function, we ensure that each one of these lines is true. Otherwise, this whole condition fails and the function is undefined. So yeah, we're checking whether the options are contained, whether gray q is a boolean, whether the radius is a positive number, whether RGB values are a repeated number of 3 positive integers, and so on. So we are putting everything into this condition. And that ensures that whatever option we pass is either valid, in which case we can apply it. We are safe to go into the body of our function, or if it's not valid, then it is caught here before anything is actually evaluated. So again, it's a good practice to try to catch things as early as possible, so you don't try to apply bad options or bad functions to bad arguments and so on. So let's do some testing now. So now that we have defined this, well, let me run those tests and let me show you what happens with each one of them. So passing an image, a valid style but not a valid option, returns undefined, and the reason is that um, when we evaluate this piece of code, uh, then this condition is checked and the condition fails because bad option goes to value is not contained in the option of image styler. So this line returns false. This and, because one of the lines is false, also returns false. The condition is not met, then we're saying to the user this function does not exist. Very similar when we have a valid style and a valid option, but not a valid value for that option. Let's go back again to our definition, see what happens. Second, we're calling blur with bad radius. So one of the lines here is we are checking whether the value for radius is a positive number. Because bad value is not a positive number, this line fails, the and statement fails, the condition fails, so we're getting back undefined function. Same thing with gray Q. Um, but what we're not handling, so we are handling bad values now for our custom options, but we're not handling bad values for bad image option values. So these are the things that we inherited from the image symbol in Wolfram language. So you could go down this rabbit hole and try to catch every single possible bad option, and you have plenty of tools at your disposal to do so. The simplest one being restricting arguments by head. Slightly more complicated is using predicates, and much more complicated is using conditions. But with that, if you really want to make your function robust to all sorts of bad input, you could go and do that. But instead of trying to of playing whack-a-mole with bad input, I would like to move on to um, something slightly more interesting. Specifically, I want to move to overloading, and if we have time, then we can talk about error handling and custom messages and so on. So let's look at overloading, which is not so much. It's not It's mainly interesting from a conceptual and kind of a functional point of view. There's not that much syntax here. Um, so it's a nice kind of change of pace. Because so far, and again, if all of the syntax that we covered here doesn't make immediate sense, then don't worry about it. That's completely normal, as I mentioned, especially when you get to more complicated things like conditions and predicates and option patterns. It might look a bit too much at the moment, but once you do it once or twice, then it gets much easier. Again, as long as you understand what the concept is, what we are trying to achieve with these things, then the syntax is actually the easy part. You can always look that up in the documentation, in the notebook materials, and so on. So let's move to overloading. Overloading is probably one of the most useful concepts that you can learn when we talk about functions. So before we actually get into the syntax, let me just give you kind of a simplified explanation of what overloading is. So as I mentioned previously, in our previous examples, when we were restricting arguments, we were saying that um, if the arguments don't match our restrictions, then the function is undefined. So what happens if we want to have a function that is defined if the argument is an image, and we also want the function to do something else if the argument is, let's say, a number? Well, the most kind of simple solution would be to write two different functions, one that accepts an image and another, a different one that accepts a number. However, there is a much more kind of simple and elegant way of accomplishing that, and that is to use the same function name but to have different definitions depending on what the arguments are. So when we say that a function is overloaded, we mean that it has more than one definition. It's overloaded with definitions, and it's able to handle different inputs in different ways. Because again, we are thinking about an imaginary function here, but if you have a function that's able to take either an image or a number, then it's probably going to do different things depending on what the argument are. It's very unlikely that the right hand side of your function will be the same um, if the input is an image, and if the input is a number. And in fact, we can simplify our existing function. So previously we were checking whether the style is blur or sharpen or RGB value with a switch statement, but that's another thing that we can handle with overloading. Essentially, we can define our function multiple times. We can define it once when the style is blur. We can define it a second time when the style is sharpen, and so on. And that's a much nicer and much cleaner, much more maintainable way of handling different input rather than have one big switch statement inside one function. So let's look at what that happens here. Now, the good thing about overloading is that you don't need any special syntax. There is no shorthand, there's no slash, semicolon, there's no arcane notation, nothing like that. If you want to use overloading, all you need to do is define your function multiple times. So yes, as it says here, a function can be converted from a switch statement to multiple overloading definitions. So this is our main function here. It's a simple definition, takes an image, option patterns, and it has a condition. It's checking whether, again, it's checking that the options that we're passing are actually contained in the options that we can handle. And then the second condition is the important one. It's checking whether the option passed to the gray queue is a Boolean. Essentially, what this means is that this definition of a function is expecting a gray queue option. So this will be the function definition that we're going to use when the user asks for a grayscaled version of their image. The next thing we're going to do is we are going to handle the different styles. So we have the first will be automatic. So if the person passes automatic as the style they want, then we have um, our basic function here, which just checks for gray Q. If the person if the person passes blur as the style they want, and again, the important thing here is the definition. We're using the same function name for each one of our examples, but the arguments are different. So this function definition is only valid when the user passes automatic as the second argument. This function definition is only valid when the user passes blur as the second argument. And you can see that the actual right hand side of our functions are different. So obviously when the user passes blur, then we want to apply blur to the image. If they don't pass blur, then we don't want to apply blur, or we don't want to apply any styling to that function. Another function definition, again, same name, but this one is only valid when the second argument is sharpen, in which case we simply apply sharpen on the right hand side. So you can see that even though we have multiple functions now, the right hand side, what the function actually does, is much more manageable. Same thing for RGB. When the second argument is RGB, we can apply that. So let's define all of those and see how they work. So the behavior is unchanged. Correct input still provides the desired results. So when we pass blur, we specify radius, that works. Um, but what happens here is that, let's say I am a user of the function that you have written, and I'm not sure what the function does, so I want to inspect the source code. So let's say I'm interested in this evaluation. How does this work? So I'm calling an image styler function with one argument that is an image and a second argument that is blur. So I go back to your function definitions and I only find the one that I'm interested in. In this case, the second argument being blur is this one. This is much easier to read, even though it's still a bit unwieldy and the code is repetitive and so on. For all of its faults, it's still much easier to read this function here than it was our huge function with the switch statement before. And again, in this case, we're only dealing with three possible styling options: blur, sharpen, and RGB. But if we had many more, then the value of overloading is even higher. Um, so yeah, and in terms of actual functionality, it's still identical as our as what we achieved before. In that we're able to handle bad input, we're able to handle bad options and bad values. So we're not really losing anything by using overloading on our function. It just makes our code more readable. So at this point, I would say that our function at this point is well designed. One, because it's very robust to bad user inputs. It has sensible default values. So even if the user doesn't pass something, even if the user doesn't pass an image as the first argument or a style for the second argument, we are able to infer sensible defaults. It's inheriting options that are useful. So things from the image options, things like resize and so on. And it's robust to bad options, bad values, and so on. And the actual definitions, even though they are repetitive in the sense that we are, a lot of this is kind of the same between different function definitions. It is still a nicer design overall than the previous one with switch statements and so on. So I would say at this point, our function is in good shape. And if we were writing this function for somebody to be using, then we can be quite happy with the result that we have so far. Now, if we want to go further, we can further in making the function nice and easy and manageable. We can get really fast with recursion and iteration. I don't think I'll have time. Let me just look at the clock. I don't think I'll have time to go in. Well, I can give you the basic idea, and then again, same idea. If you're interested in the syntax, you can look it up. Recursion is, well, I do want to spend some time on recursion because it is actually a another powerful concept that you can use in your functions. But I will still say the idea and the principle of overloading is probably the most important thing you take away, um, in terms of a principle that you can apply to your own functions. But recursion is also nice, and it's also very useful in some specific cases. But on a very basic level, a recursion or a recursive function is a function that is able to call itself. Um, and that's recursion is very useful, but it's more situational. So whereas I would say overloading, you can apply it pretty much to any complicated function or any function that does multiple things. You are able to get the benefits of it using overloading. Recursion is really really has a situational use case. So I would so I we can talk about how it's applied here, but I don't think this code is actually simpler than the one we arrived with overloading. So again, if you're interested in that, again, the basic idea is a function that calls itself. Um, you can explore the code, but I do have 10 minutes and I do want to cover a few other things as well. Uh, So as long as I give you the basic idea of recursive functions as functions that call themselves, you end up, in this case, you end up with a bit of a shorter code, but in my opinion, a code that is harder to read. So let's say that this is an optional improvement that you can look at if you're interested in recursion specifically. What I really want to get into, and the reason why and the idea is the same. If you use recursion, you can maintain the functionality of your code so it still works in the same way as it did before, but here the function definitions are even shorter. But again, in this case, this comes at the cost of readability. What I really want to get into is scoping, so I will scroll past a few things just to see whether we have whether we have a section on scoping, because that is the overloading, recursion, and scoping are probably the three kind of main things that I want to cover. I want to make sure that I cover scoping as well, because it's another thing that is a simple idea but really really useful um, in writing your functions, just from a practical point of view. So, what is the idea of scoping? Or here it's called localization, but I think you just as often you'll find it referred to as scoping. Um, the idea of scoping or localization is that when you define symbols, they are only available in the context that they should be available in. What does that mean? It means that a very common kind of pattern or mistake is when you define a lot of symbols in your notebook. Let's say you have a equals to 1, um, b equals to 2, or whatever. You define these symbols somewhere in your notebook, and then you have later on you modify them with functions, you assign different values to them, and at some point, given enough complexity, um, you start making mistakes, in the sense that you expect this a to actually equal 1 because you've defined it here, but there is something later in your code which changes the value, uh, and then the value of the variable is no longer what you expect. So a very good practice, especially when you write complicated functions, is to localize those variables that should be localized. Meaning that if we are defining a function, then we want the expressions in those functions to only be valid in that function itself. So if we have a function where we have, well, let's say in this case, positive number q, we want this positive number q to only have that value inside our function. So how do we do that? And essentially meaning that if we later on try to call this positive number q, it should be undefined because it's localized to the function itself. So how do we do that on a practical, on a kind of coding level? Different ways, actually. The most common one is module, which is why it's covered here, but you have different constructs like block as well, and different ways you can do that. But let's cover the most simple one with module. So module is a similar construct to a function, but it allows you to have a list of expressions that are only valid inside this module. So in terms of syntax, the first thing that goes into a module is just a simple list of what is going to be localized to this module. In this case, we have three different symbols that we're saying are only going to be valid in this module. So we have positive number q, RGB style grayscale. These are the helper functions that we defined earlier. Because earlier when we defined them, we kind of defined them on the top level of the notebook. So we had positive number q and we had the definition, which means that any other part of the notebook could use them, which is actually what we wanted, but could also modify them, which can introduce kind of unwanted consequences. So if we use this module structure, we're saying these will only be valid inside the module. As long as we get outside, as long as we leave this square bracket here, which closes the module, these are no longer available. So that means that we eliminate the chance of accidentally modifying their values. Um, so again, module first thing is a list of local symbols. We have a comma, and then we have the actual expression, the actual thing that is going to go um, into the module. Um, w- Once we know that positive number q is a localized symbol, then we can give its definition. And again, this definition here, whatever we give it, is only going to persist until this module is closed. Really, really important concept in making sure that your code is clean and that you are avoiding introducing bugs by mistake, because there's nothing more annoying than um, having a bug in your code, not being sure where it comes from, and then realizing it's actually something like a scoping issue where something is modifying something it shouldn't. It becomes really difficult to trace. So a module is kind of a very nice preemptive solution for that. And just to give you a simple example of what I was talking about, for example, let's say this, just to show you how modules work in practice. So we have a module, we have a list of symbols that will be local. Let me first clear this because I believe I gave it a definition. So normally, if we don't have any value assigned to a variable, Wolfram Language just returns the variable itself. If we do assign a value to a variable, then obviously every time we call it, we get the value. Um, However, if we want to assign a value to this that is only valid inside a specific place, it's localized to a specific place, we can use the module. We're saying this will be a local symbol to this module, and then we give it a definition, and then we can do things like a plus 5, which will give us obviously 1 plus 5 is 6. But the benefit of that is if we try to call a outside the module, then we don't have access to either this or any of the values. A is kind of successfully localized to the module itself. So that's a bit of a simpler example just to show you how that works in practice. Um, Let me see if there's anything else. Yeah, there are a few things that I didn't have time to cover. Um, well, I wish I had covered recursion a bit more, but also things like usage messages, because previously we were only getting errors that came from the functions themselves. Um, we can have custom error messages as well as kind of instructional messages, or telling users exactly how to use the function, which argument goes where. But sadly, we didn't have time to do that. But if you're interested in that, by all means, look at the notebook. And then finally, we arrive at the final version of our function with all of the different things that we discussed, with arguments, with options, with overloading, with recursion, custom usage function, all of that. And we can write some tests. Again, tests are another topic that probably merits a webinar on its own. But I'm quite happy that I covered probably most things that I wanted to cover, except maybe recursion. But I'm quite happy that overloading and localizations are probably more important than recursion. So I'm quite happy with that. So, and with that, I'm out of time. So thank you very much for listening. Hopefully this was useful to you. Hopefully you 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 got some ideas of things that you are able to use in your own functions, whether it's restricting by arguments, restricting options, overloading your functions, um, localizing your variables to avoid any bugs. Hopefully some of that was useful to you, and thank you for listening.